invite Gabriela, Martinez, Balbontin. Thank you very much from Mecator, Ocean International. Thank you very much. We can welcome you.
Thank you. Yes, so I'm going to talk a little bit about the biogeochemical seasonal forecast that we've been developing using machine learning. So first of all, why even do this at all? Marine biogeochemistry, as we have discussed in length, regulates how much carbon the ocean absorbs, is the basis of the food chain that supports ecosystems and fisheries, and shapes the climate. And a lot of these applications, long-term forecasts are needed for a lot of these applications. For example, fisheries could anticipate low oxygen events, harmful algal blooms, and where fish are going to go depending on nutrients or plankton. Climate scientists and policymakers could estimate how much carbon the ocean is going to take and what effect that's going to have on the global climate system. And coastal managers would be able to better prepare for environmentally impactful events. So one of the reasons why this is difficult is because traditional models are expensive, and even though they're powerful, they can be slow. And so running these long-term forecasts or ensembles is often out of reach for most operational centers. And on top of that, biogeochemistry can be particularly tricky, as we have discussed, because it involves many processes, physical, chemical, and biological, that are intertwined and that interact at different scales. We have really few observations, as it has been said before as well, and because of this, it's difficult to parameterize those models, and if they're not well parameterized, then the error tends to grow in time. So with this in mind, we developed BG4C, which is, we're working on BG4C, which is a global data-driven forecasting system. It's a modular framework that tries to leverage domain knowledge in order to build the model. So we first compress the vertical water column. We then add surface forcings. So the physics we added through forcings on the surface to this latent compression or this compressed representation of the water column. And then we add the lateral transport. We model the horizontal interactions between different local regions. And so this is what some of those forecasts look like. This was for the year 2022, I think. But here we're showing some of the variables. We have 30 variables in total because we're modeling all of Pisces. It's a full emulator. And yes, so some of the results or some of the lessons that we have learned from this is that we can achieve high accuracy at 6 months. The model beats both persistence and climatology for nutrients, oxygen, and the carbon system through 6 months. Biological variables are a little bit more difficult to predict because they change faster. And this is consistent with what we see in the literature, but this is work in progress, and we're looking for ways to improve this. Scale is preserved at depth, so the model is still useful below the surface, which is also useful. And as I mentioned earlier, the model receives physics forcings, because in order to predict the biogeochemistry, we need to know what the physics is doing. And we have developed another version as well, which can generate its own physics, so that it doesn't have to be dependent on another model. And this is interesting because that means that we can run it both ways. We can either take the physics from another model and see what the biogeochemistry, how it behaves or how it forecasted, or we can use our own physics that are generated with the same model, and so that makes it independent. Some other lessons is that because this is a modular framework, we can use the compression separately, and this is independent from the forecasting, so that itself can have its own applications. Each different module can be developed separately. So as I just mentioned, the physics, we can develop that separately, our own physics forecaster, or take some physics forecasted by somebody else. And this is independent from the other modules. And because the model is, the unit for the model is the water column, it makes it easier to just generate regional predictions because we are not dependent on the global grid. And also developing this model, we have learned some insights about biogeochemical predictability. So yeah, one of those interesting results is that most of the predictable signal is encoded already in the water column itself, but horizontal coupling can matter at longer forecasting horizons. And the next steps include developing ensembles, because for now the model is deterministic, and as we know, that tends to blur things, so we want to have ensembles. And we want to have ensembles where we can incorporate observations, so do data assimilation into the model. And of course, targeted upgrades or updates depending on what the community needs. Thank you.
Kind of a general question. The next step for this development would be what, and maybe couple that with a question that I asked earlier, what is maybe a challenge or a risk to pay attention to?
So because right now the model is emulating another model, it's going to inherit all of the biases that come from that model, and we want to bring it closer to observations. But because, as we have seen, there's uncertainty that that comes from the observations and that comes from the model, we want to develop things in a way that we can account for that uncertainty and also communicate it, because we're making forecasts, so it's good to give a range. Yeah,
it's another example of we can't just let the tools develop by themselves, if I may say so. We have to take into account the previous bias and put that through a human intellectual digestion, if I may say.
Yes.
Yeah. Thank you very much, and let's welcome you back to the floor. It's been a pleasure to listen to you as well. And